Thank you, Pauline, and big thank you really to the RSC for inviting me to chair this meeting. Before I introduce our outside on the coffee tables. This is the weather magazine for the Weather Club, and as Pauline said, I was founder of the Weather Club in 2010, so this is a relatively new concept. It's the public outreach arm of the Royal Meteorological Society, so it's a fun and interesting way to find out about the weather. So pick up one of these, and if you want to find out more, have a chat with me over coffee at the end. So I'm delighted to be able to welcome you all and introduce Peter, who's here to talk tonight. This is the second time that Peter has actually made an appearance here at the RSC. He was here back in May 2010 when he also chaired a lecture, so maybe I'll return in a few months' time and actually give you all a talk myself. I've known Peter and I've worked with Peter over a number of years, and but I'll take you back a little bit to when Peter was a child and grew up in the Lake District. Again, another northerner like myself, but probably from the wrong side of the Pennines, as I would say. But again, I think the weather in the Lake District is probably another place where you'll see so much variety of weather going on outside your window. And I guess Peter has a kind of a number of outdoor hobbies as well, so clearly how the weather impacts on his life as he was growing up and as he became an adult was something that made him want to kind of ask those questions about why do these things happen. You obviously know Peter yourselves because you've seen him as a BBC weather presenter, and he's been doing that now for a number of years, but also he does Gardener's Question Time, so you'll have heard him on the radio as well. Peter graduated at Newcastle University in 1979, and that's another thing that I've got in common with Pete. We both graduated at Newcastle, although I think you were probably a decade ahead of me on that.
Yes, certainly.
And shortly after that, he went not only to spend time working, but also living in the Antarctic as a meteorologist for the British Antarctic Survey, and I think maybe we'll get a feel for that during the talk tonight. He was responsible there for taking weather observations and balloon soundings at the Brunt ice shelf. And if you can imagine, particularly during the winter months, the darkest months of the year, temperatures falling to -40 degrees, having to go outside to do balloon ascents and to take weather observations, it was probably a rather challenging time, I think, for Peter. He finished his time at the Antarctic in 1982, and for those of you who remember, this was around the time when the Falklands War started. So Peter was trying to get back to the UK actually during a kind of conflict in the South Atlantic. But he managed to finally make it back to Southampton on the first ship that was returning out of the war zone, and made it back. And at that point he then joined the Met Office as a weather forecaster in 1983. And he's had a variety of careers before he headed off to do television work. He was a forecaster for the Tornado jet pilots. He did rocket trials in the Outer Hebrides. And amazingly, it says here, he was forecasting the conditions for chicken farmers in Norfolk. Maybe something you could chat about with Peter over coffee later. The BBC Look East, which is based in Norwich. And he moved to the BBC Weather Centre 4 years later in 1997 and has been there ever since. Obviously working on various TV channels within the BBC, BBC One, and as the BBC expanded onto the interactive channels and BBC News 24, the team at the BBC expanded and Pete grew with that, and has probably seen a number of changes at the BBC over the years, with changes in graphics, the data and the information that we use, which again I'm sure will come out in the talk tonight. So obviously Pete's got a lot to say about being a weatherman, so I'll finish there and let Pete come up and tell us all about his talk tonight, which is on the next few days to the next few decades.
Thanks very much, Liz, for that kind introduction and for pointing out I was a decade ahead of you at least at Newcastle. Thanks very much. I must admit to feeling slightly nervous lecturing in the sort of inner temple of chemistry for the UK, because I have to admit I can't even put a chemistry O-level to my name. Having said that, I certainly had plenty of interest in the subject in my youth. Came near to blowing up my father's shed on a couple of occasions, mixing various things together to produce hydrogen, to produce bangs, and copper plating nails in copper sulfate solution, I can remember. But what I could never get to grips with was the way that chemical formulae worked. You add a bit of this to a bit of that, and you get 2 of those and 3 of these. It never seemed to me, personally, to have enough logic to it. So I suppose perhaps that's why I ended up in the very exact and logical science of weather forecasting. Next few days to next few decades. I should really call it next few hours to next few decades, I suppose, really, but the alliteration wasn't quite there. But what I will be looking at is perhaps the surprising similarities in techniques that are used when forecasting the weather over periods from the short term right out to decades ahead. And I think that might surprise some of you. Let me set it up by giving you a fictional but believable scenario. So you're in the Today studio, waiting to do the weather forecast. And on a daily basis, we have to perform the miracle in the Today studio of doing a detailed weather forecast for the whole of the UK in 1 minute and 30 seconds. That's if the presenter hasn't asked one more question just before the weather forecast, which they are prone to do on occasion, because we're not allowed to crash the pips at the top of the hour. It's not done on Radio 4. So I'm sitting there in the studio, and Sarah Montague is doing an interview down the line with a reporter, and it just happens the top story that day is severe flooding in the Midlands. So this reporter's up to their knees in the floods. Sarah Montague's interviewing them, and I'm getting a bit nervous because I'm looking at the time and it's getting a bit close to my allotted moment at 3 minutes to 8, and she doesn't look like she's going to finish. But she sees me looking daggers at her, and so finishes the interview. Which means that we're over to John Humphreys to hand over to the weather. And he gets an evil glint in his eye and looks across and says, "So before the weather forecast, Peter, just tell me, these floods, global warming or not?" So now not only do you have to do the weather forecast in 1.5 minutes, you've got to explain all the intricacies of weather forecasting over periods of short term and how that links into what's happening over the longer term. And it certainly needs more than 1.5 minutes to do that, but hopefully I can take you through at least some of that through this evening. So where do we start? Weather happens on very different timescales. At Wimbledon, you're worried about the shower that's coming along that might last perhaps for 15 minutes, half an hour, and suspend play. Then you're looking at weather systems that might take 2 or 3 days to develop over the Atlantic and span hundreds of miles in terms of area that they actually affect. You then move on through seasonal periods. This winter's a good example. Think about last winter. End of December, we'd had the coldest December in the record. This year, we've had some remarkably mild weather, and there's daffodils flowering, and I can't get my head around that. As a Gardeners Question Time chairman, it's not right. And then add all that together, and you have the challenges of climate change, which looks at decades into the future, and trying to get a handle on what we could expect to happen over that sort of timescale. So, same elements, but over vastly differing timescales, and different problems that each of those bring. And it's not easy science, meteorology. This is a situation back in February 2009 across the southwest of England. What you're looking at is a snapshot of a radar picture, which essentially shows the intensity of what's falling out of the sky at that given moment. So the brighter the colours, the more intense the precipitation. Now I say precipitation because it's not all rain. Some of it was snow. That very bright area you see in Torbay, just to the west of Exeter, was producing snow and rain. There's a road that goes out of Exeter towards Plymouth that goes up a hill. At the bottom of the hill it was raining heavily. At the top of the hill it was snowing heavily because of the drop in temperatures as you go up a little bit higher. and one lorry jackknifed, and that was it. The road was blocked. So just imagine, that's a relatively small area. If that had been placed a few miles one way or the other, or temperatures were just a degree or two higher overall, there wouldn't have been a problem. And that's the sort of challenge we face on a daily basis when we try to predict the weather. We're also unlucky in the UK, and it is one of the most difficult places to forecast in the world for the UK, to get it accurate, that when it does snow, it tends to be right on the cusp. The sort of temperatures we have in the UK were right on the boundary of the phase change between solid and liquid. It tends to snow around about freezing in the UK. If you're in the middle of Canada this time of the year, then if something's falling out of the sky, you can be fairly certain it's going to be snow. Also this year it has been a bit odd actually, but that aside. So here we can see the blue areas where it's expected to snow, the green area is where it's expected to be rain. There's quite a sharp dividing line. You're trying to give advice to the rail authorities, the road authorities, as to where they're going to have problems with snow, and it's a very, very fine line. So again, we're dealing with those sort of judgment calls on a daily basis. And whatever you say about weather forecasting, economic forecasters would give their eye teeth to have the level of accuracy that we have in weather forecasting. I don't seem to remember too many warnings of the cyclone that hit the financial world a few years ago. So we don't do a bad job. How do we do it? Well, to start with, before you can do any weather forecasting, you have to know what the weather's doing at that particular moment. You have to get a picture of the weather before you can actually start to try and predict what it's going to do. And we do that in a number of ways. Surface observations, Liz mentioned that I served my apprenticeship in the Antarctic, taking daily weather measurements. Well, that's done all over the world. Some of it by people going out and opening a box and reading thermometers, although increasingly it's becoming automated these days as technology makes that more possible. But one thing strikes you straight away: the coverage is very variable. Across developed areas of the world, there's quite dense coverage. Across the less developed areas, then it's much sparser. And as you might imagine, central parts of South America, for example, central parts of Africa, the observations are few and far between. And then across the ocean areas, which are important areas in terms of weather prediction, then it's even more sparse. So that's immediately a problem in getting that first picture of the global weather before you actually try to predict it. We can fill in some of the gaps with radar, at least over the land areas and adjoining sea areas. Weather radar is quite clever. It was first noticed, I think it was back in the 50s, when some of the radars used in air traffic situations noticed that they were picking up strong returns from advancing weather fronts, which wasn't a good thing because it actually blocked the radar. What the radar does that looks for weather now is select a frequency that doesn't just bounce back from water droplets or ice crystals, it only has partial reflection, because if it all bounces back, then you only see the leading edge of what's coming towards you, you don't get that whole picture. So there's a frequency is picked which will actually only do a partial return from the water droplets and from the ice crystals. Some of it goes on to reflect from further crystals behind those initial ones, so you get a much better picture. And that's quite a powerful tool, but again, limited in area. You can't have weather radars out over the oceans very easily. But it fills in some of the gaps between the observations. And of course, weather doesn't just happen at the surface. It is a very three-dimensional thing, and it's important in setting up that initial picture of the state of the atmosphere that you have the three-dimensional picture. That's done by releasing balloons, by and large. The network isn't as dense as the surface observation network, but again, over developed parts of the world, it's reasonable. Balloons are released twice a day. In most cases, but again, you get into the oceans and they're few and far between. There are some ships these days, though, that are equipped with automatic balloon release systems, so they'll pop one off every now and again as they're going their way across the ocean. And aircraft have increasingly become an important source of upper air information as well. over the last 5 to 10 years. Most commercial airliners now, particularly the long-haul ones, will have an automatic system on board which continuously measures the weather parameters and sends them back via satellite to the data collection centre. Now, okay, there are only certain parts of the world where you have these flights going back and forth, but we're quite fortunate that a lot of them in the Northern Hemisphere tend to run through the areas where we get the jet stream. The jet stream is very important in determining the weather that comes in across the UK, because that's the driving force for the big depressions that come hurling across the Atlantic and into the UK. So we can get good information from aircraft on one of the most crucial parts of the whole weather forecast jigsaw. So it might not look very extensive, but it's quite well targeted. And increasingly over the last 10 to 15 years, weather satellites have become a hugely important piece of the jigsaw. Again, filling in the gaps. This is the latest Meteosat satellite, which is European. It's a geostationary satellite, part of a whole network that sits, I'm sure you know what a geostationary satellite is, but just in case you don't, it stays in the same position over the Earth. So it rotates at the same speed as the Earth at a distance far enough out that it can maintain that orbit, and it means you can sit a satellite over a given point and just keep taking constant pictures of that point. And at the moment there are 5 satellites. The Americans have 2, because of course they would. The Japanese have 1 and the Indians have 1 as well, and that gives total global coverage on a very regular basis. And that's the sort of thing that you get as a result. Again, filling in the gaps, giving us lots of information, and actually since the age of satellites we've learnt some new things about weather that we'd never probably have picked up without that view from space. Fog, for example, when you've got a large area of fog, it actually disperses from the edges inward. So just like a puddle evaporating in the sun. That wasn't known before the advent of satellites, but now we know that if you've got a location in the centre of a large area of fog, that's going to be the last to come out of the fog, and that's very useful if you're forecasting, say, for an airfield. We've also seen the big storm that came through in 1987 that caused all the damage. That had a particular cloud signature. There was a particular shape of cloud that developed on that as it was deepening out to the west of the UK, called a baroclinic leaf, to give it its technical name. But that's something that wasn't known about before the advent of satellites. Now it's something we know to look for in a powerful storm that's developing, and that just gives us confidence in the forecast. I just put this one in because it's a rather pretty picture. This was the big storm that hit Scotland early December, when there were winds gusting to well over 100 miles an hour. They closed most of the schools across Scotland, particularly through the central belt. You can see the big eye of the storm out over the North Sea. The UK is not easy to pick out, but that sharp back edge to the cloud, that's the cold front that was driving southwards behind the actual main storm system, and it had a very, very straight back edge to it. I took quite a nice picture over my house in Berkshire of the back edge of that thing clearing away, and it was nice to relate the satellite picture to what you could actually see from the ground. But very, very powerful tool, and something that's really just come about over the, as I said, the last 10 to 15 years, really. So we've got all this information. We've got a good idea now of the state of the atmosphere at a given point, but we now want to know what the weather's going to do as a result. If you're going to go out, you want to know what time it's going to rain. There's a very simple way of doing that, but I'm going to need your help to actually demonstrate it. So I'm going to ask for 3 volunteers from the audience. You didn't know, did you? You're going to have to work for your supper this evening. 3 volunteers just to help me demonstrate a simple way of weather forecasting. Don't all put your hands up at once. Come on, who wants to come up to the front and just... Yes, thank you, madam. Start the ball rolling. Just 2 more. 1 more, yeah, lovely. Just 1 more. Lovely, thanks very much. Thank you. Thanks for volunteering. Okay, can I ask your name, madam?
Leslie.
Leslie, would you like to stand over here for me, please? That's lovely. And I'm told I have to put you behind the table so that the cameras can see you. Thank you, Leslie. And Jennifer. Would you like to stand in the middle there, Jennifer? And Dominic. And Dominic, if you could take up your position on the end. That's great. Okay. Don't look too worried. It won't hurt a bit. So we've got 3 people and we've got 3 locations. You'll be pleased to know, Leslie, you're living in the beautiful surroundings of Pembrokeshire. In Pembroke. It's a place that rains a lot, though. Sorry, I've forgotten your name. Jennifer. You're going to be in Bristol. So, nice city. Great Britain. And all that. Yeah. And Dominic, you're here, I'm afraid. You haven't gone too far. So you're in Piccadilly at the end of the lecture. Well, I mentioned in Pembroke it tends to rain a lot. So Leslie, you're outside in the garden and you're looking up at the sky and the wind's picking up and the clouds are beginning to look a little bit threatening. And sure enough, as you look out to the west, the westerly winds are freshening up. Then it's just that first few spots of rain. Can you feel that? You can feel those first few spots of rain. Okay. So immediately, of course, you get out your iPhone or your BlackBerry and you put out a message. You look at your watch and, being a good observer, you note that the rain has started at 2 p.m. Right. If I get my clicker, I'll put that on the screen. So, 2 p.m. in Pembroke, the rain was falling on Leslie. Now you're out and about in Bristol doing your shopping, and you're a follower of Leslie's on Twitter, aren't you? Of course. And you notice that this tweet came out at about 2 p.m. and you know the wind's coming from the west, so you're thinking, there's a chance that rain might actually arrive in Bristol before I've finished my shopping. And sure enough, looking up towards the sky, before you get back to the car, you feel a few spots of rain coming along. Did you feel that?
Yes, I did.
Yes? Okay. And you look at your watch, being another good observer, and you see that it's now 5 p.m. So the rain's travelled from Pembroke to Bristol in 3 hours. Now, Dominic's come to the end of the lecture here in central London. He was hoping to get back to the tube, nice and dry. He's a follower of both our other volunteers on Twitter. So he knows that the rain's got to Pembroke, got to Bristol. So Dominic's looking a little bit worried as he comes out at 8 o'clock at the end of the lecture that it is going to rain. But Dominic is now prepared, because Dominic knows the rain is coming and he knows it's going to take another 3 hours to get to Piccadilly. So Dominic stays dry and looks very smug. That, ladies and gentlemen, is continuity forecasting. It's something I have used when I was forecasting for the RAF. It can work over periods of maybe a few hours, but beyond that it gets a little bit difficult. Thanks very much for that. I hope you didn't get too wet. Thank you. Round of applause to our volunteers. Thanks very much. Thank you. That's lovely. So, continuity forecasting, the very simplest form of forecasting you can possibly have. Oh yes, I should have said 8 p.m. But it has its limitations. A weather system can intensify, it can speed up, it can slow down, it can decay. And if you're looking for a forecast for the next day or beyond, then continuity won't do it. You may be looking at weather in 2 days' time that hasn't even developed yet out over the Atlantic. So that's the basic concept, but we need to go a little bit further than that to actually do a better job of weather forecasting. And this was the man who realised there was a much better way. Lewis Fry Richardson, fascinating man. He realised that you could do it by maths. That if you divided the atmosphere up into a grid, knew the starting conditions at each of those grid points, you could then apply simple equations of state, so phase change of water, for example, and equations of motion to move things on into the future. And you could do those calculations for each of those grid points and then get the state of the atmosphere, say, in an hour's time, 3 hours' time, 6 hours' time, 3 days' time. And he recognised that this was the way forward. Problem was, he was doing this back in the 30s and 40s. And his first attempt, he tried calculating a single 8-hour period of weather, and it took him 6 weeks. And it was wrong. So that wasn't a very good start. But he did postulate this possible way of doing it, and I just want to read you some of his words. The forecast factory is what he came up with. And he says, imagine a large hall like a theatre, except that the circles and galleries go right round through the space usually occupied by the stage. The walls of this chamber are painted to form a map of the globe. The ceiling represents the North Polar regions, England is in the gallery, the tropics in the upper circle, Australia on the dress circle, and the Antarctic in the pit. A myriad computers, and when he says computers, he means people with slide rules, because there wasn't such a thing as a computer at this time, are at work upon the weather of the part of the map where each sits. But each computer attends only to one equation or part of an equation. The work of each region is coordinated by an official of higher rank. You can see the sort of area that he worked in, and the days. Numerous little signs display the instantaneous values so that neighbouring computers can read them. Each number is thus displayed in 3 adjacent zones so as to maintain communication to the north and south on the map. From the floor of the pit rises a tall pillar to half the height of the hall, with a large pulpit on its top, and in this sits the man in charge of the whole theatre. He's surrounded by several assistants and messengers, and one of his duties is to maintain a uniform speed of progress in all parts of the globe. In this respect, he's like the conductor of an orchestra, in which the instruments are slide rules and calculating machines. But instead of waving a baton, he turns a beam of rosy light upon any region that is running ahead of the rest, and a beam of blue light upon those who are behind. So beware the blue light. Or somebody will be around there with a whip to tell you to speed up with a slide rule. So, fantastic idea, and so far ahead of its time, because essentially that's what happens now within a supercomputer. We have now got the technology to be able to do exactly what Lewis Fire Richardson envisaged, and do it very well. But it does require enormous computing power. Vast numbers of grid points, huge amounts of data, and of course time is always against you because the weather doesn't stop. You've got that starting position, but that starting position is changing all the time. You have to run ahead of that to try and get ahead of the weather so you can get a forecast out in time to actually be of benefit to people. And not just a few hours ahead, but we're talking about several days ahead. And we're also well ahead of the theoretical physicists in having a unified model. We don't rely on things like neutrinos going beyond the speed of light, but the unified model that's used within the Met Office, and most of the stuff I'll be talking about in the next short part of the talk is based on the Met Office modelling, but it means that the same computer model can be used for virtually all scales and all time periods from the next few hours right up to the next few decades. And I'll talk now a little bit about how that actually works. So we talked about having lots of grids. The resolution of that grid is obviously going to be quite important, because the finer resolution, the closer together those grid points are, in theory, the more detailed your weather forecast can actually be. And just to demonstrate this, we've got 2 maps of the relief, the mountainous nature of the UK, as modelled within 2 of the main models. So on a model of 40-kilometre grid length resolution, you can see you've got a vague sort of hint of the Welsh Hills and the North Pennines and a big lump where the Scottish Highlands are, but there's not a lot of detail beyond that. And some parts of the East Coast disappear altogether under the sea as you smooth things out. On the right, you go to something with a 4-kilometre spacing, And you can see you get something that looks much more like the relief map that you'd see in an atlas. And the same thing applies to the modelling of the atmosphere above that. Again, you need the 3 dimensions to be able to do a good job. Earlier models, and up until the last few years, many of the models that the Met Office used just had 38 levels, but now we're up to 70 levels through the atmosphere, vertical slides through the atmosphere, and notice the way the levels are concentrated down towards the surface and then spaced out more as you go higher up, because the processes near the surface are some of the most important in terms of what we want to know from a weather forecast. To give you some idea of how it all works for the UK, we have a model that runs for the whole globe. So there's a 25-kilometre grid model that runs for the whole of the globe. So at those 72 levels, you have got a point on every 25-kilometre spacing all around the globe. So you can see how the amount of data just escalates with that sort of number of grid points. But to get a better idea across the UK, within that, you then nest, and that's within the blue box, a finer resolution model with a 12-kilometre grid currently, and that's known as the North Atlantic and European model. And that's, at the moment, the main sort of tool that's used for the UK forecasts. But then again, nested within that, we pick out smaller areas. This was the forecast that I picked off earlier today. That's the frame for midnight tonight. So you can see the sort of detail you get out of the NAE model. The brighter colours, just like the radar picture, showing you where the heaviest rain is likely to be. So you can see it's picking up quite nicely the heaviest rain coming in across western Scotland, because the rain is enhanced by the fact that it's being pushed up against the mountains, orographic enhancement as it's called. The isobars show the winds will be going around to the northwest as that pushes through. Further south across southern England, the sort of white and grey areas are the amounts of cloud. So the white areas are telling you it's going to be cloudy. The greyer areas are showing where cloud is likely to be more broken. So quite a lot of detail on there across the UK, and that's the basic tool that you will then see translated into the TV forecasts when you see the moving areas of blue and the moving areas of cloud. That's directly taken from this model and fed into the BBC graphics system. So it's quite sophisticated. And again, we have the 3-dimensional aspect to it. This is essentially a graph of temperature against height as you go up through the atmosphere. And again, this is for this evening and tonight. There are warnings out for wind gusts up to 60-65 miles an hour or more across northeast Scotland for this evening and tonight. And the reason for that, you'll notice the way if I just wander over there, you'll notice the way the temperature falls with height up to a certain point and then begins to rise again. That's known as a temperature inversion. And what tends to happen if that inversion point is just above the tops of the mountains, as it is tonight across the Scottish Highlands, then the strong winds blowing through actually get squeezed into the gap between that inversion, which tends to trap the air, and the mountains below. So you actually get a sort of Venturi effect, and the winds are accelerated across the tops of the mountains. So we could well see winds in excess of 60 to 70 miles an hour across the tops of the Scottish Highlands tonight. But again, that's the sort of detail, and that's the sort of important information that we're getting from numerical weather forecasting as envisaged by Lewis Fry Richardson. And the quest is on to go ever finer in terms of resolution. This is the UK4 model on a smaller area, but this is 4-kilometre grid spacing. So now we're getting really down to fine detail. And you can see the level of detail is looking a bit more like the sort of stuff we were seeing on the radar picture a little bit earlier. There's an awful lot of detail in there. Now, the challenge for the forecaster is that not all that detail, because it's a prediction, is going to be necessarily correct. So you're getting more information, more detailed information, but the job of the forecaster, and this is why forecasting is still very much a person-machine mix, is to pick out the noise from the signal within that output. And we're actually going all the way down now in the latest model to 1.5 kilometre resolution, which was not even dreamt of several years ago. Certainly when I started weather forecasting 20 odd years ago, we'd never have thought we could get down to that sort of resolution. But it's all as a result of the increase in computing power that's allowing that to happen. And there's a lot goes into these models. They're very, very sophisticated. It's not just things like temperature, air pressure, humidity, etc. It has to take into account things like soil type, because when the sun falls on different soil types, it absorbs more or less of the heat and gives back more or less of the heat. So that has to be factored in, because all that's feeding back into the atmosphere. Not just the type of soil, but actually the moisture content in it. If you've got very wet soil, that will take a lot more of the sun's energy to heat it up. It'll also release moisture through evaporation, so that will feed back into the atmosphere. So all these factors are included in the model. Type of vegetation. Tree cover reflects the sun's radiation in different ways to grass cover, or desert, of course. And that is adjusted on a seasonal basis, because, of course, leaves come and go through the northern and southern hemisphere outside of the tropical region, so that has to be taken into account. Sea surface temperature is quite important. Warmer seas, more evaporation, more moisture available, particularly through the tropical regions. Lower sea temperatures, cold sea surface, less moisture available, and that has an impact on the atmosphere above it. That's updated on roughly a weekly basis, because it doesn't change that quickly. Sea ice, another one. Again, you can imagine if you've got more sea ice, you reflect more sunlight back, so you get less heating of the atmosphere. And even the thickness of the sea ice has a bearing on it, because thicker sea ice will reflect more strongly than thin sea ice. And even sea surface currents come into the equation as well, because areas of warmth will be transported by sea surface currents. So there's a phenomenal amount being modelled within these systems, just to give you a weather forecast for whether it's going to rain the next day, and more beyond, of course. So it's not just the dress sense that's improved since the 80s for Michael Fish, who actually has no regrets at all, of course, about the 87 storm, because it's been a nice little cash cow for him since then. He's done quite well out of it. But basically now the forecast for 3 days ahead is as good as the forecast was for 2 days ahead 10 years ago, if that makes sense. So we're a day better at forecasting now than we were 10 days ago. We'll get the same level of accuracy at day 3 as we used to at day 2. So it's moving on incrementally. So that's the next few days, and the limit of predictability really for really tying down accurate, very accurate forecast is around about 4 to 5 days. Beyond that, you start to get into things like the butterfly effect. So there's a little butterfly very pleased with himself because he's flapped his wings and knocked somebody's house down with a tornado. It's the whole butterfly effect thing is a little bit exaggerated. But what it's trying to say is that in a chaotic system, which is what the atmosphere is, small initial changes can have big impacts further downstream. I'd like to just try and explain that a little bit more. And a bagatelle board is quite a good way to think about it. A chaotic system, it has lots of variations which tend to look random. And in fact, they're not random. If you set off several balls one after another into that bagatelle board, you probably get quite different results. But of course, all the balls would go up and then fall back down again. So there is variation, but there's also some physical laws that are actually governing all that. It's still all affected by the laws of physics. So one ball might go up and hit one pin and go off in a certain direction. Another one, slightly less velocity, might hit it in a slightly different way and go off, hit another one in a slightly different way. And so the uncertainties cascade through the system. The important thing to remember is that the current state of the system always has an impact on what's going to happen in the future, although it doesn't look like it does. So how far back you pull the plunger to set that ball off has a big impact on where it ends up in the future and what path it takes through the bagatelle board. And only very, very small differences in the amount of pressure you put on that plunger and the velocity of the ball going up the chute and whether it just hits a little imperfection on its way up has a big impact on what happens further ahead and whether you get a good score or a bad score. And it's exactly the same with the atmosphere. And I think we can demonstrate it here. Don't worry too much about the details of this, but essentially all you need to know is that it's a contour chart of temperature, is essentially what it is. So the blue areas are cold, the green area is sort of middling, and the red area is quite warm. So that forecast out to a day ahead would suggest that the UK is going to be in a warm area. It's going to be in some warm air, and the cold air is going to stay up over Greenland. Forecasting 3 days ahead, then you start to see a little bit more variation in that. They're called spaghetti charts, these, for fairly obvious reasons. It'll become more obvious as we go into the next one. But you can see again, despite the fact there's some uncertainty there and some variation, you've still got essentially warm air across the UK, you've still essentially got that colder air over Greenland and northern Canada. Once you go out several days further, now this is out to T plus 168 hours, so I can't look at that off the top of my head, but it's certainly over a week, yes. And you're getting a lot of divergence now. Lots and lots and lots of different solutions. And yet, you can still see within that a basic pattern. It's still mostly cold air up across the northwest, the top left of the map. It's still mostly warm air pushing up towards the UK. But now you'd have a little less confidence because you could easily be in the sort of green zone across the UK. Perhaps just as likely to be in that as you are in the red zone. So the confidence in the forecast is decreasing as you go further ahead, as the chaotic nature of the atmosphere kicks in and the difference in the initial starting conditions has that impact downstream. And this is called ensemble forecasting. And it's probably the major development in weather forecasting, I would say, over the last few years. There's a group called the ECMWF, the European Centre for Medium Range Weather Forecasting, based in Reading, which was set up several years ago by a group of European national meteorological centres, and that is their brief, to develop medium range weather forecasting out to 10 days and hopefully out to 15 days. And they have developed this technique of ensemble forecasting. So what you do is you have your basic computer model and you run it 50 times. But each time you run it, you change the initial conditions just slightly. And that's actually a harder thing to do than you might think, because most models have a lot of stability in them. So you can try tweaking a few things, and if you just then run it, the model will say, no, I'm not having this, and it'll revert back to it'll smooth out those little imperfections you've made. So they have to do some fairly sophisticated maths to do the perturbations, as they're called, in the initial starting conditions. But essentially, they change it and run it 50 times, and you end up with 50 different answers. But, very often, a lot of those answers will look quite similar. And in these charts, for example, a lot of them have, like this one here, I know they're not easy to see, but basically it's got quite an intense area of low pressure out to the northeast of the UK, strong winds coming in from the north or northwest, so you could be fairly confident in that particular setup that you would see some cold air coming in. And as you look around, you find that actually the majority of those 50 solutions come up with something along those lines. There's the odd one, like there's one here that the winds are much weaker. There's one where they're actually a bit more sort of west to southwesterly, so that would give you something a little milder. But they're in the minority. So what that does is give you a bit more confidence that your forecast this far out can actually be believed. Now, it's still possible that that might be the correct one and all the others might be completely wrong. But it gives you more confidence that the majority are going to give you the right sort of solution. And that's very, very useful for decision makers. Equally, if every one of those look completely different, surprisingly, that can actually be quite useful information as well. Because that's telling you that the weather is in a very unpredictable mode. And it does this. It goes in and out of levels of predictability. Sometimes the weather seems to be very predictable and you'll get good, solid, consistent forecasts, even several days ahead. Other times it's in a very sensitive condition, and that change in initial conditions can make a huge difference down the line, and then you know that you can have less confidence in those predictions. And that can be a useful thing for decision makers as well, to know that there's much less confidence in the forecast that far ahead. And you can pull out diagrams like this just to give you some idea of how that's used further. This is called a whisker diagram. So you've got your 50 different solutions, the little box on the left there. The max is one extreme of all the different solutions. The min is the other extreme of all the different solutions. The bulk of them are in that square box in the middle. That's 50% of the forecast fall within that box. And so if you look through this, it's called a meteorogram. So we've got temperature here, we've got wind speed, we've got precipitation, we've got cloud cover at the top. Just look at the precipitation one for a moment, and you'll see that you could be quite confident there probably that you are going to get some rain in the short term. But notice the way the box is very elongated. That means there's quite a big spread of rainfall amounts in the forecast. So some of them think there's going to be quite a lot of rain, some of them think it's not going to be very much. So with that big spread, you're thinking, okay, well, I think I can be confident it's going to be wet, but I can't tell you exactly how much rain there's going to be. Whereas on the temperature, they're much more squashed up. That means all the solutions are much closer together, so you could be much more confident that the temperature at this point was going to be around about that sort of level. So it's a very, very powerful tool. So that takes us out to 10 days. They're trying to push it out to 15 days. But the level of predictability, the limit of predictability, because of chaos, seems to be around about the 10-day mark currently. And probably won't change very much, to be honest, even with more sophisticated models. Beyond that, you get into the realms of seasonal forecasts, which, as a Met Office employee, I have to be a little bit careful about. Seasonal forecasts are tricky things to do. It's probably the hardest area of forecasting currently because there are so many variables. You're going beyond that 10-day level. You're going out several weeks, sort of 3-month periods. Somewhere like the UK, of course, we get huge variability over seasons. As I mentioned, last winter compared to this winter, massive difference. And that's very difficult to actually pick up. Now, there are some parts of the world where seasonal forecasting is somewhat easier. Through the tropics, for example, you have well-defined wet and dry seasons as the line of shower cloud moves northwards and southwards across the African continent, across the South American continent. Those seasons are quite well-defined. Through the temperate regions, like the USA and across northwest Europe, it's very different. Weather systems come and go. There's a lot of... You get the wind from the north and it goes very cold, you get the wind from the south and it goes much, much warmer. And the UK is right on the crossroads of all that. We get essentially 4 different influences. You get the continental influence from the east, which gives us cold weather in the winter, hot weather in the summer. You get the moderating effect of the Atlantic, so if the winds are coming in from the west, it gives us mild winters and cool summers. Anything from the south is particularly warm, but if it's from the southwest, it's moist. So we're at a crossroads of lots and lots of different weather types. That does make it very, very difficult to pin down. But as I say, other parts of the world, it's a little easier. And the rhythms laid on top of that seasonal change, and I'm talking here about things like El Nino, which you've probably heard of, which is this fluctuation in the sea surface temperatures in the Pacific, have quite well-defined, they're known as teleconnections, but well-defined impacts on the climate in various other parts of the world. So during an El Nino year, for example, you would expect the rainy season across northern Australia, across Indonesia, Southeast Asia generally, to actually be much drier than normal, because all the warm water is across the other side of the Pacific. So you can make quite a strong seasonal statement on the result of just knowing that you've moved into an El Nino situation. There are also some impacts on North America, which seem to be quite robust. An El Nino year will give a wet and a cool summer across southern parts of the USA. It'll keep it very warm up into Alaska and northwestern parts of Canada. Unfortunately for the UK, there seem to be only very tenuous connections with things like El Nino here. There's some suggestion, there's some correlation with perhaps warmer, drier conditions across the far northwest of Europe during an El Nino, but it's fairly tenuous. So all that means that for the UK, we have to use different methods to give seasonal forecasts, and they're not, at the moment, terribly robust. So we will use computer models. We'll use exactly the same models as we use for weather forecasting, run them out over that seasonal period, over 3 months. Now, you're obviously not looking to see if a particular date is going to be hot, dry, wet, sunny, or whatever. What you're looking for is the overall trend and the overall averages through that period. And you should get some sort of steer from that, even with a day-to-day weather forecast model. You use the ensemble techniques that we talked about. So you change initial conditions and run it out several times and see if you get any sort of agreement on that to try and give a level of confidence. And then you add in these statistical methods, which are things like, is there a connection, is there an El Nino year, is it a La Nina year? And you add all those things together, and quite often you don't get anything terribly revealing. Or not to hang your hat on. You know, that's the sort of result you might get. So the summer's going to be above average temperatures, well, about 50% probability of that, which means there's a 50% probability of it being average or below. And unfortunately, the way these things work, it can be that the solution is in the below average category, even though that's the lowest probability of all. So it's a development area, very much so, seasonal forecasting. And it'd be a great one to crack, but it's going to take a lot more work yet. 2 minutes, okay. And then we go a bit further into the realms of climate change. And you'll hear, of course, talk about models being used to model climate change into the future. And again, you may be surprised to know they are essentially the same models as I've been talking about that are used to predict the weather on a day-by-day basis. And that may seem odd. But in fact, those models have been well proven. They do a good job of predicting the weather day to day. So there's no reason why they shouldn't predict lots and lots of weather over long timescales and the average effect of that. Again, you're not going to, because of chaos, know what the 15th of December 2023 is going to be like, but you should be able to pick up trends from that. It's not quite as simple as that. It's not just the basic model that we use. It's much more of a combined model with other aspects brought into it, and that's when we come back to the unified model aspect. If you think about sea temperature, for example, on the day-to-day modelling, the sea temperature only changed on a very gradual basis. So if you chuck in the sea temperature once a week, that's fine. If you're trying to predict climate changes over decades and centuries, then obviously there is going to be a much bigger change in terms of sea temperature over that period, and you have to bring that into the modelling. You have to actually model that yourself as part of the whole process. So lots of extra things are brought in to produce what's called an Earth system model. Just to give you an example, though, of why that can still be a very, very valid thing to do, summer 2003 was the hottest on record across many parts of Europe, and thousands of people died as a result. Crop failures all over the place. The graph here is the red line. The black line is the average temperature of European summers from 1900 through to 2003. The red line is the values from the computer model, so the climate model of average European summer temperatures over that whole period right through to the end of the century. Now, you can see it doesn't get every year exactly right. The red and black lines don't tie up on a year-by-year basis, but the overall trend is very, very close. Then 2003 sticks out like a sore thumb. So the model didn't get that, did it? No, but it's telling us that the trend beyond that is upwards. So what we can infer from that is that the summer of 2003, by 2045, is likely to be an average summer in Europe. And by the end of the century, you'd be dying for a summer as cool as that. So even with long time scales, running the same model, you can still get useful information that can put current climate in context with future climate. So just to come back to where we started, were the floods caused by global warming or not? We still can't really answer that question. But I think you can see there's a lot of tie-up between the methods that we do use for short-term forecasting and the methods for climate change. And what we can say with confidence as a result is that if our predictions of climate are correct, then instances of severe weather like this become more and more likely. Still difficult to pin down an individual event to the change in climate, but these sort of major events become much more likely. And just to finally finish off, I said that was a hypothetical situation in the Today studio. In fact, I had a very similar one for real, where Jim Naughty, for once, finished early, which is virtually unheard of. The barbecue summer forecast had just been issued, and John Humphreys really did turn to me with a glint in his eye and say, "So, Peter, the summer's going to be really warm. How do you know?" I'll leave you to think what the answer might be. Thank you very much.
Wonderful. Right, time for questions. We've probably got about half an hour. So we have 2 mics that are coming round. So if you can please wait till a microphone comes to you. And if you could then stand up and give me your name and then your question, please.
She's going to get her own back now.
Jennifer Goldsmith. Although you work for the BBC, you've probably seen on television the regional programmes like ITV Regions when they're doing the forecast for, say, the London region. What modelling do they use to be able to predict, as they say, the northwest of the region will have rain, whereas to the east it's going to be drier, for example? What modelling do they use to try and split London up into sort of very portions?
Exactly the models that I've been talking about here, the finer resolution ones, particularly now the UK4 model with the 4 kilometre spacing. That's what we're hoping to get into the graphic system before too long. At the moment we use the slightly greater grid scale, but it is very good, particularly if you've got a well-marked frontal system coming through, for example, a well-marked band of rain. It will usually pin that down really very, very well. Where it's a little more difficult is with showers, because showers still have a fairly random element to them. They're very predictable in terms of a large area, and across the UK as a whole, you can pin down really well where you expect the heaviest showers to appear, say on a county-by-county basis, but it's then very difficult to say it's going to, say, rain in Reading and not in Newbury on that scale. So it depends what you're watching, but I actually work for the Met. All the presenters at the BBC are Met Office employees who work as a unit at the BBC, and we use the Met Office model data in the BBC graphic system. That's all integrated. So it's all the same database. So if you see somebody doing the local London forecast, they will have exactly the same graphics, exactly the same database as somebody doing the whole national picture. The ITV is also provided by the Met Office, the data. They tend to use a slightly different approach in their forecasts, but essentially that's the same forecast as well.
Okay, I've got a question here.
My name is Brian Duke. Could you say a little, please, about the effect of the jet stream upon our weather? Okay.
A lot of people are very interested in the jet stream in forecasts. Since we started mentioning it, I must say when I first started at the Weather Centre, there was a great reluctance from the BBC for us to get into technical sort of language. They didn't feel the general public were ready for it. we were rather keener to talk about things like jet streams, etc. That's now changed, and we are doing much more explanatory stuff and talking about features like that. Essentially, the jet stream it's on the boundary between cold air to the north of the UK and warmer air to the south. And where you get a big thermal contrast like that, the stronger the contrast, the stronger the winds along that boundary. Now, the reason it doesn't flow from warm to cold, which is what you might expect, is that the spin of the Earth diverts the wind. It's Coriolis force is the name of the phenomenon that makes it bend, makes it change direction. And so you end up with a flow along the line of this thermal contrast. Now, why that's important for our weather is that's the thing. It's a high-level zone of wind. It's around sort of 35,000 feet up in the atmosphere. But what it does is determine where the large areas of low pressure actually move. So with a strong jet stream, you tend to get an area of low pressure forming at the left exit from the jet. So if I stand this way around, if we've got America over here and Northwest Europe here, the jet stream's piling across the Atlantic on this northwest corner of the jet stream is where you'd expect to get an area of low pressure developing. So if that area moves across the UK, that will steer an area of low pressure right across our part of the world. So that's why the jet stream is so important. It's the steering factor for all the proper weather that we get. You want?
Take a question here, please.
My name is Jeff Bull. The previous topic reminded me of an article in a very recent issue of New Scientist. I just went through it very briefly, but it mentioned another type of airstream that's recently apparently been discovered at lower altitudes, something like animated airstreams. What am I thinking of? That is associated with carrying a lot of moisture and drops it on us.
Oh, yes, atmospheric rivers. Mm-hmm. Yes, which was responsible for the major floods in Cumbria a couple of years ago. Yes, that's right. Kind of, I suppose, tied in with the jet stream to some extent, isn't it, Liz? But it's like a conveyor, really, of very warm, moist air. The warmer the air is, the more moisture it can actually hold. And what you sometimes get is a very persistent weather pattern, which has a flow of air from the tropics, or certainly the subtropics, down to the south of the Azores, up into the vicinity of the UK. That air carries an awful lot of moisture, and as it comes up against the Cumbrian hills, as I know only too well, as it rises, and rising air cools, produces moisture, and that falls out as rain. So if you get a very persistent pattern like that, and a very moist flow like that, then you can just keep dumping rain in the same area. And in this case, it was about 36 hours worth of very, very heavy rain. And interesting, our model picked that up extremely well. There were very timely warnings of that event, even down to the amount of rain that was likely and the topography that it was likely to impact on. Because that comes into the equation, of course. If it had been, say, 15 miles further south or further north, it wouldn't have fallen into the same catchment to run down that particular river into Cockermouth. So it's crucial stuff. But yes, I saw that same article, and it's an interesting feature.
I'll take a question at the front first, and then there's one at the back after that.
My name is David Murphy. You listed an interesting, impressive number of variables in how the model works and what goes into it. Is there also a sort of feedback to what's actually happened in the previous hour, 8 hours, 24 hours, that refines the next series of predictions? And is that constantly done for the immediate prediction, and then also adds to confidence in the overall efficacy of the model by looking how effective it's been? Absolutely,
and that's one of the newer techniques. You're kind of shunting back and forth all the time. It's not just here's all the starting point, now run it through. I had to keep it relatively simple to sort of stay within the time limit on this, but that is one of the newer techniques. I can't remember what technique actually...
4D VAR.
Yeah, that's it.
It's a variation.
That doesn't help, does it?
It includes a time variation as well, which is the 4D effect.
So you are constantly putting in new observed information, and you run it forward, but then you run it back again to see how it was compared to the new information you've had in, and so that shunting back and forth gives you exactly what you're talking about there.
I think
refines
as well,
the accuracy.
you get model runs coming out every 6 hours, and you can see solutions flipping back from one solution to another, and as you go forward in time, I mean, it starts to steady itself out, which gives you confidence in what's going to happen as well. So I think that's the worst case scenario, is when it shifts from one scenario to another every 6 hours, and your message then to the public is very difficult.
And it comes back to that predictability thing again. The Scottish storm early December was hugely predictable. It was fantastic. 5 days out, the model had this big deep low going over northern Scotland, and it stayed rock solid right up to the time it actually happened. And then just before Christmas, I don't know if you may have seen on some of the broadcasts, we used something new. We had another system that was initially 5 days out, expected to run up across northwest Scotland, and as we got a bit closer, it started flipping and was running up the English Channel. And we were getting flipping back and forth between, it's going to be northern Britain, it's going to be southern Britain, it's going to be northern France. And that's where this chaos thing comes into play. And that system was just so unpredictable, but we knew it was. So on the broadcast, we actually showed most likely track, but also the other potential track that some of the models were coming up with that would have had a very different outcome. So I think it was trying to manage expectations that, when I started, it was, you decided what the most likely forecast was, and that was it, you stuck to it. And if you never admitted that there was any chance of things going wrong. But we're a bit better now at actually expressing uncertainty.
I've got a question at the back.
Hello, Peter. My name's Kevin Devine. I'm very interested in the El Nino phenomenon. What effect is global warming likely to have on the frequency and the duration of these events? That's
a very good question, and one that's still trying to get an answer, frankly. I think I'm right in saying, Liz, that currently the models don't handle El Nino, La Nina events terribly well. Which I suppose you might think...
Can you predict when the next one's going to be? Isn't it roughly every 7-8 years? Or?
On average, yes.
And there are predictions that come out of the US, so you can go on the web and find them now, that give you the next few months, and they're predicting that La Nina will continue right into springtime. So there are predictions, as we do weather predictions for these out there, but again, it's like predicting the weather that far in advance. And, you go back into last year, the predictions were that La Nina would dissipate towards the end of the year. Well, it's still quite strong and still causing problems, in parts of Australia because of that. So, very much, as you say, it's a natural variability. It's nothing to do with climate change, but climate change could have an impact on the amount, the strength of El Nino and La Nina, and the frequency, and that's interesting to look at. We've got data going back on these things over 100 years or so. So there's lots of historical data about this. We've known about El Nino for a number of years, but how climate change will impact on it, big question.
But I think that shouldn't give us less confidence in the climate predictions, because it's a bit like, it's like Mark Twain said that climate's what you expect, but weather is what you get. And I think it's the same with the El Nino, La Nina thing. If you're going out several decades ahead, when you get an El Nino year, global temperatures tend to be somewhat higher. When you get a La Nina, they are suppressed to some extent. But over those long time periods, you should get that evening out, and you should still get the underlying trend coming through and reliably on the climate models.
Yes, I had a question in the middle first, if I can, and then I've got two over on the right-hand side.
My name's Ron Button. This time of year, it strikes me the freezing level is very important, but it's never or hardly ever mentioned on the forecasts. Do you know why?
Well, bear in mind that we have limited duration on weather forecasts. I suppose we do mention it in that we talk... Well, no, we do mention it not explicitly, but implicitly, because we will show you where it's likely to snow and where it's likely to be rain. And that is basically the freezing level. Now, if you had a specialist interest like going up a mountain and wanted to know what the temperature would be at the top, or where you would actually go through the 0 degree level, then that's not something that's going to be relevant to a general TV weather forecast. But there are other ways of getting that sort of information. But, in marginal situations, and you're talking about the freezing level really being down at ground level, aren't you? Being significant, yeah. And we do that because we show you the surface temperatures, and we show you when it's going to snow, and we show you when we expect it to rain. So it's implicit.
I think I had a question over on the right.
Hello. I've got a couple of questions. The first one is, has the growth of the wind power business had any effect on the business of meteorology? And the second one is, are you never tempted to go and bet on...
There's a leading question. Certainly one of my colleagues at least does often have a flutter on the White Christmas odds. But the trouble is you've got to get in before the latest forecast comes out. And you have to also be careful of accusations of insider trading as well. In fact, I remember a few years ago I did a country file forecast quite close to Christmas. And I can't remember which way it went, but I think Christmas was sort of at the end of the period, and I think I said that it was looking to be relatively mild. And it's Alex Deakin, my colleague who is into this sort of stuff. He was monitoring the betting websites, and he said, the minute you came off air, the odds on there were changing. So there is a worrying amount of power there in the weather forecast. As far as the wind power thing's concerned, there's a lot of commercial aspects of meteorology these days, and there are companies, private companies, that actually do provide a commercial service to industries like the wind power industry, and many more beside. It's definitely a growth area.
Absolutely. Yeah. I'm going to take two more quick questions, one at the front and gentleman in the red jacket, if I can.
Nick Henderson, just a couple of observations first and then a question. On the wind power basis, the amount of energy generated in the UK just before Christmas is 12.9% in wind power, which is well above the normal, just over 5%, and that was due to the storms which were coming in.
Yes.
So it's really significant.
Yes, yes.
The second comment is a heartfelt comment about weather forecasts, particularly ones on the television, which used to be accompanied by isobars and fronts and nice drawings and pictures which one could read for oneself, and which are now accompanied by grey patches moving across the topography of the country, which are impossible to follow, and one wonders whether they're actually meant to be accurate or not. And apparently statistics show that the majority of people, when questioned after the weather forecast, haven't got a clue what it actually said.
Well, yeah. That, yes.
Not a question, by the way, it's just an observation.
A lot of... No. And I think there's some interesting points in there, actually. As far as the isobars are concerned, there's also been a lot of research done on that, and despite the fact they've been on the BBC since it first started, basically, since TV first started anyway, it's surprising how few people still seem to understand what they're about. So it's still a relatively specialist audience that can actually make use of them sensibly. We do still use them. They tend to be more targeted, so you're more likely to see isobar charts on the 10:30 weather broadcast in the evening than you are on breakfast or the lunchtime, because it's a different audience, and you have to be. We have very limited duration. A couple of minutes is your average weather broadcast to do the whole of the UK. So you do have to be very targeted in what you're trying to do. The country file forecast, of course, and you get 2 forecasts now on a Sunday, full of isobar charts, and they always will be. Although I'd caution there, you see, because if you look at a 5-day forecast, the confidence in the forecast at day 5 is not as high as the confidence at day 1. And yet, the only tool we have still on TV to show you Monday as opposed to Friday is that isobar chart. And it gives to me a false sense of precision, particularly in the situation I was talking about with the, the flip-flopping of the track of the low. So I really feel strongly we need a different way to do it at those sort of timescales, out sort of 3, 4, 5 days ahead. But it's a useful tool at shorter terms. You've got now internet access. Virtually everybody tends to have access to the internet in some shape or form. Okay, not everybody I know, but it is, it is a massive information tool, and you can get exactly what you need on there. So again, we have to be sensible and careful about what we provide in our TV weather forecasts, because there are other ways of actually getting it across.
Well, thank you for that. That actually leads into my question, your uncertainty about predicting 5 days ahead. It's a very interesting lecture, thank you. You didn't say very much, in fact, didn't say anything about the composition of the atmosphere, which might lead you to answer that question. So briefly, were these floods caused by global warming or not? Dare you, in this illustrious company, reveal your own view? And you've got more than 1 minute to do it.
Are you sure? We're meant to be out by 8 o'clock. Okay. Personal view. So this is not the BBC or the Met Office, is that the case is very strong for changing climate due to human activity. The physics is very basic. Carbon dioxide is a greenhouse gas. The only reason the Earth is inhabitable is because there is CO2 and water vapour in the atmosphere. If it wasn't for the greenhouse effect, the Earth would be 30 degrees colder than it is, and the temperature here would never get above freezing, and would be a damn sight lower for most of the year. So simple physics tells you that if you add more of this gas that traps heat, you're going to trap heat. There's nowhere else for it to go. The oceans will absorb some, but that's slow, and once they've absorbed, then they can't absorb any more. It's as simple as putting an extra duvet on the bed and you get warmer. Where I think there is an argument to be had is how quickly, what the impacts are likely to be, and those are arguments that do need to be had, and there's a lot of work going on with the modelling to refine the modelling. But I think it's worth pointing out that we've been doing climate modelling for a good few years now, so we have actually got some reality to go on. It's easier with day-to-day forecasting because you can always check back to yesterday and see how it went, and so you can refine models. Over periods of decades, you have to wait quite a long time to see how good your models actually are. But we've got a reasonable time period now, and if anything, the modelling has been conservative. The changes have been more rapid than the models were suggesting. So again, from a personal point of view, I think it's an experiment that we just cannot afford to keep running.
I think we should say that next time we ask.
I'm just going to take one last question, hopefully a quick one.
Thank you. Alan Bodley. Given that the sun keeps us all warm, what correlation is there between the solar cycle and the general conditions of the weather around the planet? Is there a correlation?
It's an interesting area of research at the moment, actually, because again, there's a good article in New Scientist a couple of weeks ago, some work that's been done at, it's Mike Lockwood, isn't it? Mm-hmm. It's been one of the main people at that at Reading University. It seems that solar activity could have been quite a large factor in the cold winters that we've had recently. We talked about the jet stream. When the jet stream's running round around the planet without much sort of amplification, then it keeps driving the mild westerly winds in across the UK. When it weakens and starts meandering, like a meandering river getting down to the later stages of its flow, then the weather doesn't move through. So you can get blocked situations, as they're called, and the weather stays the same for week after week after week, which is what happened in the Moscow heat wave as well, as well as the colder winters that we had. And there does seem to be quite a good correlation between solar activity and these blocked situations. The exact mechanism is still fairly unclear, isn't it? But it seems to be to do with the mix of particles that are actually coming out of the sun during low activity as opposed to high activity having a different impact on the stratosphere, the very high atmosphere, and that somehow propagates into the jet stream. But the exact details are...
Yeah, and I think the nice thing about it is that the scientific discussion about this is now been much more open. I think in the past, people who've had their own views and predictions of that have kept very much the science, I guess, under wraps. So it's nice to get it out in the open, to get people commenting, and that'll take the science forward. So I think, as Pete said, we maybe haven't got a full picture yet, but at least it's going in the right direction. Okay, we will stop there. I think there's still tea and coffee available outside for about another half an hour. Pete's around, I'm around, if you want to have a chat about anything. Well, maybe anything to do with the weather. So thank you very much, and...
Just say fill in your feedback forms.
Oh yes, remind you to fill in your feedback forms, so if you could complete those and hand those in before you go. Thank you.